How to design a differential amplifier circuit given a target voltage gain for that differential amplifier. This example has a single stage with a core of matched BJT or bipolar junction transistors and a common emitter that is connected to a current source implemented using one JFET or junction field effect transistor N-channel type. So it's an N-channel JFET, junction field effect transistor, with the drain, source, and gate as highlighted. For input of the circuit, we have Vin equal to A sinusoid omega t, so it's a small signal, so A is a small value. It's a small signal AC analysis. Omega is a proper frequency in band, so we are not worried about that being out of band. At the output, as a result of this applied sinusoidal input signal, we also get a sinusoidal output signal. And the voltage gain, AV, which is V out divided by Vin at the input, this is the voltage gain, and let's say this is given to us as an example to be 188. It can be any reasonable value you have in mind, but as an example, let's say we target achieving this. Also given to us is the value of RC, 4.7 kilo ohm, let's say. Of course, we have some degree of freedom, but let's say this is a good starting point. The dual supply values are 10 volt VCC and also minus 10 volt in this design. So it's a dual supply design. What we don't know are the DC bias of the BJT transistors. We don't know. All we know is the circuit has a mirror symmetry around the center. So this part is exact copy or mirror symmetry of the other part. So as long as that's the case, we can assume that the DC current of the two BJT transistors T1 and T2 should be exactly equal. So I just need to find one DC current there. Now the sum of these two DC currents, so if I show the DC current, let's say in blue color, so that's the DC current IC, and of course this is the collector of transistor 1, this is the emitter of transistor 1, and this is the base of transistor 1. And the same thing, this is the emitter of transistor 2 and collector of transistor 2. Maybe I show it here. So collector of transistor 2, and then we have of course the base of transistor 2. The Vin effectively applied between the base of the two transistors exactly, using the decoupling caps that decouple the AC signal from the DC bias value that is going to be present at the base of the BJT transistors. So effectively for our analysis, we are assuming that these two decoupling caps are shorted in the AC signal frequency of interest, and of course the bypass caps are also shorted, so it means that from AC standpoint, this point is effectively AC ground. So that's the meaning of the bypass cap here. The same thing about decoupling caps here. So they decouple output. We will feel at the output only sinusoidal voltage, and we don't feel the DC voltages at the collector of these two transistors. Now, the plan is like this. The 188 desired AV or voltage gain of this differential amplifier is given. My plan is to just figure out how the circuit is operating, and from there figure out the formula for AV, and then plug in 188 value, and hopefully from there figure out the DC bias or current IC for the two transistors. As soon as I find the IC, then I can say the IDS, so the current, the DC current of the N-channel JFET IDS is 2 times IC, because of course 2 IC are flowing downward from the two transistors and add together so that it becomes 2 times IC as the drain source current of the JFET transistor. So as soon as I find that, then I can also decide about the value of R1 and R2 to make sure that the JFET transistor and BJT transistors are operating in the proper region. Recall that the IV curve of both transistors, let's say BJT, voltage of collector emitter, so this voltage, and the current of the collector for the BJT transistor, the IV curve, looks like this. And what we want is operating not in this region, which is the ohmic region. Basically, we want to just operate in the saturation region of transistors. So we would like to have the DC value of collector emitter, so DC of collector emitter and also the DC value of the collector current to be at this point, so that the sinusoidal oscillation happens just around this point. And the same thing in the sense of the IV characteristic of the JFET transistor. We know that VDS, voltage of drain source, this voltage that I just showed, and the current of drain, or the current of drain source, this current that I just talked about, the IV characteristic looks like this. So there is an ohmic region that we don't want to operate there. We want to operate and bias transistors somewhere in the non-ohmic region here. So DC voltage of drain source and DC current of IDS, so that then we have the proper setup for transistors. So we will make sure these are the case. Okay, so let's start from the output voltage. When the sinusoidal input AC signal is applied, a small signal, what happens is, because of mirror symmetry of these two matched bipolar junction transistor, half of Vin appears between base 1 and emitter 1. So basically VBE1 equal to Vin divided by 2 with this polarity. And half of the rest of the Vin, half of Vin appears with this polarity. So VEB, or basically minus, so let me put it this way, VBE2 becomes effectively, so base emitter I'm saying. So if I put it this way, plus minus is Vin divided by 2, but this is equal to minus VBE2 because the polarity is minus. Okay, so if this is the case as a result of this voltage drop, so let me put it in a different color so that it indicates AC, small signal voltage. This is AC, a small signal voltage, not DC voltage. As a result, a current base for the transistor 1, IB1, AC current, is to start flowing and becomes the emitter, and that would exactly match the counter direction current, which is going this way. So if we have a DC current like this, it's as if we have an additional small signal IC current adding to the DC current during the positive cycle at input. And during that same positive cycle, it's as if there is a current like this in absolute term equal to the value of this one. So it would be exactly IC1. Let's refer to it as IC1 is good enough, going up. So we have a loop like this. And because of this AC currents that are passing through these two transistors, it's as if we have a voltage drop, AC voltage drop like this across the RC. So let me put it this way. So as if we have plus minus AC voltage across RC, and then we have matching exact drop plus minus across this RC. So effectively, between the positive default terminal of output, which is this node, and the negative default terminal of the output, which is this node, we have two RC-IC voltage drop because of the two RC resistors. So what I can say as a result is Vout, which is an AC signal, of course. So Vout is equal to 2 times RC times IC1, which I refer to as just IC. So 2 times RC-IC, meaning that AC current. Contribution of VBE, Vin over 2 for a given transistor. So what I can write here is 2 times RC times, instead of IC, I can say, if I have the transconductance of 1 BJT GM, by definition IC is GM, or transconductance, times the voltage across base emitter, which is Vin over 2, AC voltage. So it's going to be Vin over 2. Of course, these two cancel out each other, so we get RC GM, and then we have Vin. So the only the only thing I need to do is I know RC because that's 4.7 kilo ohm that is selected. Vin is assumed to be input signal, so it's known. The only thing that I need to figure out is GM here. Okay, so to do so, let me go back to the well-known Shockley p-n junction equation. Again, I don't want to make assumption to use any memorized formula, so I'm going to go back to first principles here. So Shockley p-n junction IV equation, which is the known equation that says, so it would be voltage of base emitter of the p-n junction equal to eta, or ideality factor, which is assumed to be 1 for silicon p-n junction. Vt is the thermal voltage, so that's the, let's say, so that's the thermal voltage, which is kT over Q. K is Boltzmann constant, Q is electron charge, T is the temperature junction for the bipolar junction, p-n junction, and assumed to be room temperature. So at room temperature, this is roughly 25 millivolt, roughly. So that's the value of Vt. And then we have log of, natural log of, the current of the collector of the p-n junction, let's say bipolar junction transistor, divided by saturation current. Let's take the partial derivative of base emitter voltage with respect to the collector current. So what I get is just Vt, because assume eta is 1, and then I get 1 over Is in numerator, and then I get Ic over Is in denominator when I take the derivative of ln here. So as a result, I get that the partial derivative of voltage of base emitter with respect to current is just simply Vt over Ic. This is equation 1. Why do I need this? Because if I go back to equation that I was writing, so it's Rc, or let me put it this way, it's Vn times Rc, and Gm is simply partial derivative of the current of the collector divided by, let's say, or with respect to the voltage of base emitter, which is exactly reverse of this. So inverse of this. So we get just inverse of this using equation 1. I can substitute and I can get Vn Rc times Ic over Vt. Just the inverse of what I found here. Because we have Ic over VBE, not VBE over Ic. Okay, so great. This is, from here, if I move Vn and put it as denominator for V out AC, then exactly I get the voltage gain. So voltage gain is V out over Vn, therefore is simply RC Ic divided by V thermal. So the thermal voltage in the denominator, and then the DC current Ic times Rc. Okay, so I'm going to highlight this as equation 2. That's very useful. Now what I can do is just I can go back to the desired value of 188 and apply it to equation 2. So I'm going to use equation 2 and say, okay, I want AV to be 188. So this is equal to, and I know Rc as given to us is 4.7 kilo ohm. So I get 188 equal to 4.7 kilo ohm times Ic, the DC current of the bipolar junction transistor that I need to figure out, divide by the thermal voltage with the p-n junction temperature at room temperature, so 25 millivolt. This actually end up to be Ic equal to roughly 1 milliamp. Of course, we can write the formula for Ic as well. So if you want to write the formula using this whole thing, I can just say basically Ic is equal to the target, let's say the Vt, the thermal voltage, divided by Rc times the target voltage gain. So I just substituted for the values of these guys, and I found in this example Ic has to be 1 milliamp. So each of the DC current through these transistors is 1 milliamp. That means the sum of them, as was discussed, should be equal to 2 milliamp. So IDS DC, okay, so I'm going to write it here using, let's say, equation 3. So let me just say equation 3, which we got to the result of 1 milliamp. I say, using equation 3, I know, so basically, let me put it this way. We know that IDS is 2 times IC, the current of DC current of the JFET, N-channel JFET. And as a result, substituting for IC from equation 3, we get 2 times VT over RC times AV is just IDS. Okay, great. Which means IDS is, of course, 2 milliamp. So we know that the DC current of the JFET is 2 milliamp. But then, just keeping it as a formula so that we can use it later, we know that IDS of the JFET transistor, if it is operating in saturation region, non-ohmic region that we desire, like this region that we talked about, we know that the formula is roughly, neglecting, let's say, channel length modulation, it would be just roughly something like this. So it would be IDSS, or the let's say IDS saturation times 1 minus VGS divided by voltage of pinch off squared, roughly. So for the current voltage equation of the N-channel JFET. Okay, let's make the assumption that the JFET transistor selected here has, so I'm going to write it here. Let's make the assumption that the JFET transistor has IDSS of 4 milliamp, let's say 8 milliamp, IDSS 8 milliamp, and let's make the assumption that it's just a matter of which device you purchase or you buy from, let's say the likes of Mauser or any other distributor. But let's say the IDSS for this N-channel JFET is 8 milliamp, and let's say the pinch-off voltage is minus 4 volt. So let's say we know them. Okay, so with that in mind, and of course one of the other assumption that we assumed here for AC analysis is the RD, or let's say RC of the resistor of collector of transistor is negligible compared to, say, 4.7 kilo ohm. That's why it's not considered. So going back to the analysis I have here, I can substitute and set this to, so I can use these two values basically and set, given that I have VP, given that I have IDSS because I selected the specific N-channel JFET, and I know IDS has to be equal to 2 milliamp, then therefore we can find the DC value for VGS, which will define what would be the voltage across gate source, which means the voltage across R1, and hence we can find the R1, because for the case of R1, we know that, let me change the color, we know that there is a current of 2 milliamp. We know that there is no current going through the gate of the JFET because it's effectively just open, infinite impedance relatively speaking. So no current going this way. All the current through R1 and R2 DC current would be just in series. So there is a IDS of 2IC, which is 2 milliamp going through these two resistors. So 2 milliamp in this example, IDS. If I know the voltage drop across gate source, then I know the voltage drop across R1, and then I can find R1 given that I know 2 milliamp is going through R1. That's the idea. So going back to what I was doing, okay, I can set then IDSS times 1 minus VGS over VP squared should be equal to 2 times VT divided by RC, and then AV, which is equal to 2 milliamp, of course, in this example. But if I keep the formula just for future use, then I find that I can write what I need to find is VGS. Then I can write that the VGS DC for the N-channel JFET in this example should be equal to just VP and then 1 minus square root of, just making sure that I'm not missing something, and that would be 2 VT divided by, let's say, RC IDSS times AV. So that is the general formula that we end up having in this example for the value of the DC of VGS of transistor JFET transistor. If we substitute that, what we find is, of course, let me do it quickly here. So that would be, so let's just name this as a formula here. So that would be number 4, and then what we get is a VGS is equal to, of course, we have, just let me substitute for the values here. We have -4 for VP, V pinch off, this guy, times 1 minus, of course we have square root 2 divided by 8, so 2 milliamp divided by 8 milliamp, so these are milliamp, and it becomes just simply -2 volt. So that is the voltage of gate source in DC value. Okay, so we have voltage of the gate source in DC value, and as a result, now we have everything to find the R1. So I know the voltage drop across R1 with the polarity gate source -2, so there's a 2 volt drop across R1 when 2 milliamp is passing through R1. So therefore I can say just R1 is equal to IDS DC times so V source gate is IDS times R1, and gate source is -2, so source gate is 2 volt equal to IDS times, IDS is of course 2 milliamp, and times R1. So we find that R1 has to be equal to 1 kilo ohm. Okay, so we found R1. Great. So R1 known, and DC bias of the two transistors of BJT transistor and also the JFET transistor is known. One other thing I can quickly find is RB, but I can get to it as the last thing because it's a minor thing to find. Regarding R2, it's important to make sure that, as I said, the N-channel JFET is properly biased in this region. And in order to be in this region, not in the ohmic region of the JFET or linear region, we need to just make sure that the drain voltage is higher than the gate by absolute value of pinch off. So that is an absolute requirement. So I'm going to write it. So in order to have N-channel JFET in biased, let's say, biased in proper region, so that it operates as a current source, what we need with a very large basically output impedance at the between the drain, or as seen from the drain, which is nice thing we get in this region, then as a result we need voltage of drain to be higher than, let's say, voltage of gate by absolute value of pinch off, and in this case so that we are in the target region. So what that means, let's say this is equation say 5, I think. So from equation 5, given the pinch off is -4, absolute value of -4 is 4, so V drain is greater than V gate by 4 volt at least. I would like to also show what we can expect from the behavior of, again, IDS VDS characteristic for this transistor, I mean JFET transistor. This is just the illustration, just the optional thing. So on this side you can see ID versus VDS. So on x-axis we have voltage of drain source, ID is on the y-axis. So we can see, depending on the value of gate source voltage, whether it's 0, -1, -2, and ultimately at -4, which is, since -4 equal to pinch off, if voltage of gate source for this JFET, N-channel JFET is -4, transistor turns off. There you go. It shows that the current is 0 for this curve. And of course, for another view is the ID versus VGS. So what we expect is the highest ID value equal to IDSS of 8 milliamp, as mentioned, happens when voltage of gate source is 0. And then as we are reducing the gate voltage so that VGS is dropping, then the current is dropping in a nonlinear fashion, as you can see. And then finally, when VGS gets to -4, which is pinch off, then we can see that the current of drain, or IDS, of the transistor, of the N-channel JFET transistor, gets to 0. So at -4 VGS, we get to 0 milliamp for the current. Okay, so this was exactly what I was referring to. So that's the behavior, and that's the characteristic, IV characteristic of the N-channel JFET. So let me move this out of view. Now, given that VD should be greater than VG plus 4 volt, I understand from this point that if you go up, we just found that the IC DC current for the BJT is 1 milliamp. Let's make the assumption that beta, or HFE, for these BJT transistors that are a small signal transistor is at least 100. If that is the case, that is equal to I collector over I base. So if collector is 1 milliamp, that means from these two guys, we understand that the base DC is just 1 milliamp divided by 100, which is then 10 microamp. So my understanding is there is 10 microamp DC passing through the base of each of these transistors. So 10 microamp. And the drop across, the DC drop across RB is just 10 microamp times that RB. So if I select RB to be 1 kilo ohm, we have a degree of freedom there. I mean, depending on what other criteria you have in mind, you can select different value for RB. But if I select RB 1K, given that there is a IB of, say, 10 microamp is passing through it, then it means the voltage drop across RB is just simply 10 millivolt, because 1K times 10 microamp is 10 millivolt. So all I'm trying to say is the voltage of base, given here is grounded, the voltage of base will be roughly -10 millivolt, which is negligible. We can assume that the voltage of base of the DC voltage of base of BJT is roughly 0. So I'm going to write it here. I know that with RB selected to be 1 kilo ohm, and given that I base, which is IC over beta, is 1 milliamp over 100, which is 10 microamp, then I know voltage of base DC is just on the order of -10 millivolt, which is roughly 0. So I can say, since base is roughly 0, the emitter of the common emitter of the two BJT transistor will be roughly at -0.7, so because that's the turn-on voltage for the PN junction of operating properly biased BJT transistors. So, but that voltage of emitter is the same as the drain of the JFET. So what I can say is, therefore, voltage of drain is roughly -0.7 volt. Okay, then I have equation, say, let's refer to it as equation 5, and then we have this one as equation 6. So I can apply 5 and 6 combined, and then I can get -0.7 greater than V gate plus 4. So I get V gate should be less than -4.7 volt. Okay, what is the benefit of this? Well, V gate is this center node between, or this middle node between R1 and R2. Okay, I know that I can find the value of this V gate as a function of voltage drop across R2 and the minus VCC of minus 10 volts. So I can write, therefore I can write this. I can write voltage of gate equal to minus VCC plus the R2, the voltage drop across R2, which is R2 times IDS. So as a result, I know this is equal to minus 10 volt, and then IDS is 2 milliamp, so plus 2 times 2 milliamp times R2. And then combining these two, since I know VG should be less than minus 0.7, it means this value, which is VG, should be less than minus 0.7. So minus 10 plus 2 milliamp times R2 should be less than negative 4.7. So from here, I conclude that 2 milliamp times R2 should be less than 5.3 volt. And as a result, we conclude that R2 should be less than 2.65 kilo ohm. So that's what we needed to find. For the last remaining component in this circuit, R2, we just found that in order to keep JFET in the proper region of operation, DC biased, we need with the R1 selected 1 kilo ohm with the 2 milliamp passing through the R1 and R2, then we need R2 to be less than 2.65 kilo ohm. So let's say we set it to just 2 kilo ohm, for example. So as an example, I mean, it's just a matter of your choice now. But R2, for example, we can set it to 2 kilo ohm or 1.5 kilo ohm as an example. So this would be the conclusion of figuring out the value of the proper value of components in this single stage differential amplifier, and also properly setting up the BJT and JFET transistors for this circuit to achieve the target voltage gain of 188. I hope that this example is helpful in terms of illustrating how we can design a single stage differential amplifier. Thanks for watching.